Welcome to the new section on the quantum Fourier transform and its applications. The quantum Fourier transform is a quantum algorithm or quantum subroutine that is a key ingredient for tasks like quantum factoring, phase estimation, and many other interesting quantum algorithms that have real-world practical applications. It is, in fact, an algorithm for performing a Fourier transform on the complex probability amplitudes of a quantum state. So just like how a Fourier series, a regular Fourier series, is an algorithm that takes one sequence of numbers into another sequence through by multiplying by cosines and integration. The quantum Fourier transform is basically a quantum mechanical version of that. However, one thing that's very important to understand from the beginning is that it does not really speed up the task of calculating the Fourier transform of classical data. And we really just have to look at our previous section on the gate model for quantum computing to understand why. That will become more obvious as we progress into our understanding of the quantum Fourier transform. Rather, instead of helping us to calculate the Fourier transform of classical data faster, the quantum Fourier transform allows us to solve a set of interesting problems faster than known algorithms on a classical computer. This is unlike the Deutsch's problem that we looked at in the last section, because Deutsch's problem does not have any obvious real-world application. In other words, it's a contrived problem and not an interesting problem. Nevertheless, Deutsch's problem illustrates many of the ideas behind how the quantum Fourier transform works. And we'll come back to those ideas of Deutsch's problem as we study the quantum Fourier transform. So to be a bit more concrete, the quantum Fourier transform is important for a number of useful and difficult to solve problems. One of them is called phase estimation. This is an important application of the quantum Fourier transform. It basically allows us to approximate the eigenvalues of a unitary operator. And this can be solved faster than on a classical computer. This is useful. The algorithm phase estimation is useful in several other problems. One is the order finding problem, which we will discuss. It's a problem in discrete math. Another one is the factoring problem for decomposing a product of two primes into its prime factors. This is thought to be classically intractable. Yet another problem is for finding the eigenvalues of a unitary operator. And last, phase estimation can be used for counting solutions when combined with the quantum search. And in all of these problems, phase estimation outperforms classical versions of the same problem, the classical algorithms for the same problem, There are even more applications of the quantum Fourier transform. One is to solve the hidden subgroup problem. This is a generalization of phase estimation, which, remember, in the last slide we defined as the algorithm that allows us to estimate the eigenvalues of a unitary operator. This hidden subgroup problem is more complex than phase estimation, but it's useful because it allows us to solve another problem, which is called the discrete logarithm problem, which is also thought to be classically intractable. So, certain mathematical transformations are used often because they allow us to take a problem and transform it into another problem that we know how to solve. The discrete Fourier transform is one such type of transformation. In fact, the discrete Fourier transform takes one set of complex numbers, x0 through xn minus 1, where there are n entries, and outputs a transformed set of complex numbers, y0 through yn minus 1, which is also a sequence of length n. The values y0 to yn minus 1 are defined by the following formula. Y sub k is equal to 1 upon the square root of n times the sum from j equals 0 to n minus 1 of xj, the input coefficients, times a phase e to the 2 pi ijk divided by n. So here k is the index of y, j here is the index being summed over for the input data, and I is just the square root of -1. And we divide this phase by n, which is the number of entries in the sequence. So this should look, of course, very familiar. The discrete Fourier transform is a typical tool used for analysis of linear differential equations, for example. And of course, it is known to be the transformation that converts a function in a spatial or temporal coordinates into spatial frequency or regular frequency coordinates.